The second half of 1.7 is about compositions of functions or composite functions. And so what a composite function is it means that we take one function and we put it in as the input into another function. Now, we have done a little bit with this already, like in section 1. I want to say it was 1.4, where we had something like f of x equals, I don't know, x squared minus 3, and then we wanted to know what is f of x plus 5. So we put x plus 5 into this function and made it the quantity x plus 5 squared minus 3, and then, expanded that and combined like terms. So that's a composition of functions already, where we take the function x plus 5, which we could just say g of x is x plus 5, and we put it in as the input into f. Okay, two different notations for compositions of functions. One of them is with this little open circle here. When we read that, we just say of. Okay, so this says f of g. It looks like fog, all right? It's different from just the dot that means multiply, though. And then this is the same thing as saying f and then using the parentheses for of. So either way, we read this f of g of x. So we would say f of g of x. Okay, and you can have a composition of more than two functions. So I could have f of g of h of x if I wanted to, okay? And that would be h as the input into g, and then the output of g as the input into f. Okay, so the domain of the composite function, f of g, is the set of all x that satisfy these two things. First of all, x has to be in the domain of g, the inside function, and then also the output of g of x has to be in the domain of the outer function, okay? And we will get to some examples in a minute here where we look at how do we restrict the domain, because I know especially that second piece that can be a little bit confusing, okay? All right, so, and this is just kind of a visualization to help us with the domain. We will come back to this when we get to a domain question. Okay, so first of all, we have two polynomials. Polynomials are nice because the domain is all real numbers, no matter what goes inside another one. So this first thing is asking us for f of g of x. Now, I am going to write this as f of, and then I'm going to put g of x as this on the inside. So I'm going to write it as f of 2x squared minus x minus 1, because that then tells me this becomes the input that's going to go into f of x for any value of x. In this case, it's going to replace that. So I'm going to do 5 times and then this whole quantity. So 5 times 2x squared minus x minus 1. Okay, and then I still have a plus 6. Okay, so I have 5 times that quantity x, or not x, but the input, 2x squared minus x minus 1, and then plus 6. Now, I do need to simplify this, so I'm going to distribute the 5. So we have 10x squared minus 5x. And then here I have a negative 5 plus 6. I'm going to go ahead and combine that. If you want to do it in 2 steps, you can. I just did in one. So here is my function for f of g of x. All right, now g of f of x is going to look a little bit different, because now I'm going to write this as g of, and then I'm going to put f of x in as the input here. So g of 5x plus 6 is what we're evaluating, okay? And then this is going to be equal to, so now I'm writing g, but anywhere I see an x, I replace it with the entire input, 5x plus 6. So that's 2 times the quantity, 5x plus 6 squared, minus, and use parentheses, the quantity 5x plus 6 minus 1. Okay, so now we have some expanding to do. So that's 2 times, and then when I square this, I have square the first, so 25x squared, multiply them, 30x, and double it, so 60x, and then square the last, so 36. Okay, minus, I'm going to distribute the negative here, so minus 5x minus 6, and then I still have the minus 1 right there. All right, so multiplying the 2 here, distributing that to everything, I get 50x squared. Now this is 120x, but I'm going to subtract the 5x, so it's 115x. And then 2 times 36 is 72, minus 7 is 65. If you want to do that part in more than one step, you are welcome to do so. Okay, this one, g of f of 2. Now we are doing a composition, but we're also evaluating that composition. Now, I'm going to write this as g of f of 2 in this notation, because I think it's a little bit easier to see what's happening, like which one we do first. We can do this a couple of different ways. We already know what g of f of x is. It's this right here. So we could just plug 2 in as the input into all of that. But those are numbers I don't necessarily really want to deal with. So what I'm going to do is I'm just going to find f of 2 and then make that my input into g, okay? As a number, not as a variable expression. So f of 2 would be 5 times 2 plus 6. That's still on the inside. So that's g of 16, okay? So 10 plus 6. And then that's going to be equal to 2 times 16 squared minus 16 minus 1, which is 256 doubled, 250 doubled would be 500, so 512 minus 17 is going to be equal to, take 12 off, 500 minus 5, so is 495, okay? So if you are evaluating a composition of functions of a numerical value, just plug that numerical value into the inside function first and then do the outer function. Don't worry about doing a composition in terms of x and then plugging the number in, because that's a little bit more algebra than is necessary. Okay, so let's use some other functions, do a couple more examples. If you would like to pause it and try it and then resume and see if you got the same thing I did, that would be a good idea. So here I'm going to do f of, and then g of x is my inside function, so f of the quantity x plus 3 all over 6, okay? And so f tells me to multiply that by 6 and subtract 3, so I'm going to do 6 times that whole quantity minus 3, and that's going to give me, so I'm going to reduce those 6's, so I have x plus 3 minus 3, which is just x, okay? What this tells me, by the way, the fact that the output of the composition is equal to just x, that tells me that f and g are inverses of each other, but that's something that's going to come up later in a different chapter. Oh, nope, in the next section. Okay. All right, so then for g of f of x, again, I'm going to write g of, and then I'm going to put f of x on the inside, so 6x minus 3, and that's equal to, so g tells me to take that quantity, add 3, and divide the whole thing by 6, so 6x minus 3, and then plus 3 all over 6, which 6x, and then this is 0, divided by 6 is just x. Once again, because they're inverses of each other, the output is just an x, okay? And then lastly, for f of g of 9, now we already know what f of g is equal to. It's just equal to x, so I could just say this is going to be equal to 9 and be done. But let's say we hadn't already done number 1, okay? So I'm going to write this as f of, and then g of 9 is going to be 9 plus 3 over 6, which is 12 divided by 6, which is 2. And then 6 times 2 minus 3 is 12 minus 3, which is 9. So we got the same thing. Okay, then the next part of this is excluding values from the domain, which I mentioned before. So let's go back to this picture for a second. So what we see here is we have an input that goes into the inner function, which is g. Okay, so g is the inner function, and f is the outer function. So in order to go into function g, it has to be in the domain of g. So let's say that g was something like 1 over x minus 4. Then 4 could not go into that input, okay? The output we get from this, becomes the input into the outer function, okay? So now whatever that output is, it has to be in the domain of f. So let's say f was something like the square root of x minus 5. Well, if the output for some number, not 4, because that's not an option, let's say we plug 2 into this and we get an output of 3. Okay, so let's say 2 goes in, g does something to it, and then we get an output of, actually, yeah, ignore this because that wouldn't be the same thing. Let's say we get an output of 3. 3 has to be in the input, but 3 would give us a negative number under our radical, so that's not going to work, meaning 2 can't be in the original input, okay? So we're looking for two different things. We want to know what values would make the inside function not exist, meaning zeros in the denominator or negatives under a radical, and then also what output values of the inside function would give us an inner value, I'm sorry, would give us an input into the outside function that does not exist. Okay. Kind of messy unless we're talking about specific functions. So let's look at this one. So we're doing f of g of x. So let's go ahead and write it out first. So this is going to be f of, and then g of x is 1 over x. Okay, so that's 4 over x plus, nope, sorry, 4 over the quantity 1 over x plus 2. Now I'm going to simplify this by multiplying again by my my least common denominator of the inside fraction, which is x. I'm going to do that on the top and bottom. So that gives me 4x over 1 over x times x is just 1 plus 2 times x is 2x. For the second part here, we need to find the domain of f of g. So I'm going to start with my inside function g to figure out what can I not have. So since g is 1 over x, x cannot be equal to 0. Okay? Now, the output of g cannot be something that makes my original function have a value that's not existent, like a 0 in the denominator in this case because of the fraction. So I also need to know, well, if my f of x is x plus 2, let's set that equal to 0. Okay, x can't be negative 2, but here's the thing, it's not x that can't be negative 2, it's the output of g of x that can't be negative 2. So I'm going to take negative 2 and set this equal to g of x, okay, which you don't need to write the g of x, you can just write 1 over x, but I'm putting that there so that you can see, like if you look back at your notes later, you'll know where that came from, okay? So I'm setting negative 2 equal to 1 over x because the output of 1 over x can't be negative 2. So if I solve that, I get x equals negative 1/2. So x cannot be 0. It can also not be negative 1/2. Okay, so our domain then is all the values except that, which I'm going to write in interval notation this time. So negative infinity to negative 1/2, and then negative 1/2, negative 1/2 to 0, and 0 to infinity. So that's our domain. Or again, you could just say all real numbers except x does not equal 0 or negative 1/2. Okay, so go back to this negative 2 here. I want to make sure this is clear. Negative 2 would make, if x was negative 2, then f of x would have a 0 in the denominator, and that doesn't exist. However, x equals negative 2 plugged into the f of g function doesn't actually give me a 0 in the denominator. It would give me, if I plug negative 2 into that, I would have negative 8 over 1 minus over negative 3, which is not equal to something over 0. Okay, so negative 2 is fine. However, if I plug in negative 1/2, that makes my new denominator 0. Okay, and that I can't have. Okay, and then also I can't have 0 because of the original 1 over x issue. Okay, so let's do another example of this, and then we'll do some compositions from graphs. So we've got f of x equals x squared plus 1, and g of x is root 2 minus x. So first thing, we're writing the function, the composition of the function. So this is equal to f of root 2 minus x. Okay, and so f of x tells me I need to square the input and add 1. So root 2 minus x, that whole quantity squared, plus 1 is going to be equal to 2 minus x, because the radical and the square cancel out, plus 1, which is equal to 3 minus x. Okay, so what can we not have? Well, in the original g of x, okay, so we're looking at domain now, g of x has 2 minus x under the radical. 2 minus x has to be greater than or equal to 0, okay? So I'm setting this greater than or equal to 0, okay? And we can do this a couple of different ways. You can subtract 2, then divide by negative 1. I'm just going to add x to both sides. So this becomes x is less than or equal to 2. Okay, so x is less than or equal to 2 is my original domain. Now let's see if any output from there gives us a problem with f. Well, f has a domain of all real numbers because this is a polynomial. So there are no additional restrictions for f, meaning the domain of the composition is just this, or in interval notation, negative infinity to 2 inclusive. Okay, last examples here, we're going to use the graph. Oh, nope, sorry, next to last examples. We're going to use the graph to evaluate compositions. This is just like the problems up here where I suggested if you haven't already found the composition function as a function yet, just take that number, plug it into the inside function, and then whatever you get out, plug into your outer function. So do this numerically, not in terms of trying to write equations, okay? That's a lot more algebra than necessary, especially if we're just looking at a graph, okay? I don't really want to try and write the equations for those, even if I could, doesn't really matter. So this is going to be equal to, and then I need to know what g of negative 1 is, because that's my inside function. So g of negative 1 is, according to this graph, negative 3. And then I'm going to plug negative 3 into my outer function f. So negative 3 has an output right here of 1. And that's all I need to do. Okay? Pause the video, try the other ones. So this one is f of, and then g of 1. G of 1 is negative 5. Okay, then plugging negative 5 into f of x, I get an output of 3. So that equals 3. Okay, this one, g of, and then f of 0 is 2. And then g of 2 is, it's this point right here, negative 5. Okay, then lastly, g of, and then f of negative 1. So f of negative 1 is that point there, so 1. And then g of 1 is negative 5. Oh, back up for a second. This one was incorrect. This is negative 6. Sorry, I didn't go down to that point right there. So negative 6. Okay, now actually the last thing. Decomposing functions. So if we have a function that can be written as a composition already, we might need to be able to identify the inside and outside functions. And if I haven't said it already, compositions is a really huge issue going especially beyond pre-calc, okay? So it's important that you understand this, but also it's important that you're able to decompose a function. So you're able to find a convenient way to separate into an inner and outer part. So there's definitely multiple ways to write a composition, but we're going to look for what we would consider the natural way, kind of the way that breaks it into simpler functions, okay? And I'll give you an example of multiple ways to do it here in a second, okay? So if we're looking at h of x and we see this whole thing, we kind of see the grouping symbol here and we see an exponent on the outside. So a convenient or a natural way to do this would be to make the entire inside function 2x squared minus 4x plus 2, just that polynomial, and then make the outer function just x cubed, raising that to the third power, okay? So we would say if h of x is equal to f of g of x, then that means g of x is the inside 2x squared minus 4x plus 2, and f of x is x cubed. Because if I take this and plug it into this, I get that. Now, could I have also said, well, what if g of x, I'm going to write it over to the side and then delete it because we don't need it, but what if I said g of x was 2x squared minus 4x? Well, that's fine. That would make f of x equal to the quantity x plus 2, because I would need to take this, the g part, and then I would need to add 2 before I cubed it. That would be a silly thing to do. If I already have a polynomial, I should keep that plus 2 as part of the polynomial and then use the exponent as the outer part. Okay, so again, we don't need this. That's not the natural way to do it. All right. So here I would suggest you pause it, look for a way to try and break it apart where g of x is your inside function and f of x is your outside function. Okay, so for this one, if this is h of x, my inside function is this. So I'm going to say g of x is equal to x squared minus 9. And then the outer function, f of x, is what's happening to x squared minus 9, which is we're taking the cube root of that value. So my outside function is cube root of x. Okay? And then this one right here, my inside function, so this is h of x, my inside function is the expression, the polynomial in the denominator, so 4x plus 5, and my outer function is what's happening to that whole denominator, which means it is dividing 1. So f of x is 1 over x.